recording. So just a couple of reminders. Participation question is open. It's open through Sunday. Particulate homework. Actually, it's gas removal. Sorry, I should have changed that. Gas removal homework on absorption and incineration is due next Friday. I'm just going to make that due on the official last day of classes. Also a reminder on the final report and the poster. Those of due are on April 30th. Just a couple things in terms of logistics. You should have gotten an email about the closed forms. Those are online. And it's just a link. Laura Taylor sent those out. I'll do a reminder on the weekend weekly message. You also should have gotten this morning an email about the Withrow forms. Those are the Withrow Teaching Excellent Award. And those were sent out to all juniors and seniors in civil and environmental engineering. So you should have gotten that. If not, you can feel free to email me. I can send you the link. And then all the SIRS forms are online. So you should have gotten a link from the registrar's office or an email with the link from the registrar's office so that you can complete the SIRS forms online. So let's return to adsorption. We had just solved one problem where we were looking at the adsorption of carbon TED. And what I want to do now is to go through a little more on adsorption design. We're not going to do any extensive design, but what I want to do is make sure that I cover the material that is on the FE exam. So what I've shown here is an image with a number of columns. And really what you want to think about this is sequentially in time. So what happens, okay, we start running an adsorption column. And we've got the initial concentration coming in. And as that gas, or it could be liquid, moves down, then what's happening? So the contaminant that we're trying to remove moves from the gas, or it could be the liquid phase, onto the solid adsorbent. And this over time, within a region, equilibrium is achieved. So for instance, if we were to put a sampling port right here, and once equilibrium has reached, then the concentration that we would observe at that point is the CN concentration. So essentially there's no additional removal within that zone. This zone here we'll describe as delta, so that's the depth of the adsorption zone. And over time, what happens is that adsorption zone moves down the column. So here we had one equivalent of one adsorption zone. Here we have a second adsorption zone. You can see here. Now we essentially have three adsorption zones. And now we have four adsorption zones. And right here, we have CN, and what is concentration leaving that column would also be essentially CN. So at this point, the reactor, okay, this adsorption column has become exhausted, or what we refer to as exhausted. And typically we refer to that as the point where the concentration in the effluent is 95% of the influent concentration. Now we can also have what we refer to as a breakthrough concentration. This typically is could be a regulatory limit, it could be an operational limit. But typically we don't operate these columns to complete exhaustion. We operate it to a break point or breakthrough. And then what we would do is we would take the reactor offline and we would regenerate the column. So this time to break through can be calculated from the height of the bed. So this is the height of our bed. The depth of the adsorption zone, that delta, and the velocity at which the adsorption zone is moving down the column. Okay, so how fast is that adsorption zone moving down the column? Another thing to recognize is the smaller that delta, so if we have a small delta, what we typically will see is a very sharp breakthrough curve. So this is our C breakthrough, this would be C exhaustion. So this is a small delta, a small depth of adsorption zone. If we have a large delta, then we typically will see a much more shallow breakthrough curve. Okay, now the challenge with that, as you can see here, and I'm just going to change colors to try and emphasize this a little bit more. You can see here, if this is the time or the volume to be treated, it's could be really the volume of water that we treated is some volume, I'll call it V. But if we have a much more shallow breakthrough curve, I'll call this V2, and typically there, the V1 is going to be much greater than V2. So we can actually treat a larger volume to that point where we achieve breakthrough. And that's important. Activated carbon, in some cases can be inexpensive, but in other cases, depending on the contaminant that you're removing, can be quite expensive. Now, the height of the adsorption bed is determined in a similar way to what we used for adsorption. Absorption towers. It is also a function of the shape of the adsorption curve. And if you remember, okay, I didn't spend a lot of time going over this, but we talked about isotherms. So this equilibrium line is that X over M or Q value obtained from your isotherm data. And your operating line is based on your initial concentration. So what is in the influent gas or aqueous stream, and your effluent concentration. So what are you trying to achieve? The equilibrium line that's shown here is actually a Langmuir isotherm. Now this velocity term, so this velocity term right here, is dependent on a number of factors. So this K and this A value are the constants from the Langmuir isotherm. Q sub G is the gas flow rate, and it's a mass flow rate. So it's mass per time. This Cg star is the equilibrium partial pressure that's from the isotherm. We have a density of the solid and liquid, so as for the solid and gas, so your fluids and your solid media. and the cross-sectional area of the bed. So let's look at this example. And I'm not quite sure. Okay, there we go. Okay, so let's look at this example here. Actually, I'm going to use the highlighter first. So we're looking to determine the breakthrough time. We have a bed that is 0.5 meters, that's Z, and is 10 meters squared in cross-section. We have a gas flow rate of 1.3 kilograms per second. We have a gas temperature, pressure, so we've got the density of the air. We've got the packed bed density of our adsorbent. We have an inlet pollutant concentration. We have our Langmuir isotherm parameters, and we have the depth of the adsorption zone. And that would be determined empirically or provided by the manufacturer for a specific contaminant. So let's add a slide in here. And we'll change colors. Okay. So let's just write down all of the parameters that we have. So Z is 0.5 meters. Cross-sectional area is 10 meters squared. Gas flow rate is 1.3 kilograms per second. That's of air. The density of the air is 1.184 kilograms per meter cubed. The density of that solid, the packed bed, is 420 kilograms per meter cubed. The inlet concentration is 2.0 grams per meter cubed, or 2.0 times 10 to the minus 3 kilograms per meter cubed, so we have the same units. A is equal to 18, that's our Langmuir constant, and K is equal to 124. And we're told that the depth of the adsorption zone is 0.03 meters. Okay. So the velocity of the adsorption front is QG times 1 plus K CG star over A rho S times rho G times the cross-sectional area. So that is equal to 1.3 kilograms per second times 1 plus 124 times 2.0 times 10 to the minus 3 kilograms per meter cubed. And we will divide that by 18 times 420 kilograms per meter cubed times 1.184 kilograms per meter cubed times the cross-sectional area. And that is equal to 1.8 times 10 to the minus 5 meters per second. Yes. What we're asked to find is the breakthrough time. And the equation for the breakthrough time is equal to Z minus delta over the velocity of the adsorption zone. And that is equal to 0.5 meters minus 0.03 meters divided by this 1.8 times 10 to the minus 5 meters per second. And that is equal to 26,111 seconds, or 7.25 hours. So that would mean every roughly 7 hours, 7.25 hours, we would need to shut down the bed and we would regenerate. Now, could we lengthen that? Well, if we were to double the bed, so if we double the depth of the bed, so now Z is equal to 1.0 meter, that means we have a breakthrough time of 15 hours. So all I've done is I've gone through the calculations and calculated a new breakthrough time. So the velocity doesn't change, only the breakthrough time changes, because this would become 1. What if we were to double the cross-sectional area? Well, if we double the cross-sectional area, that changes because we have cross-sectional area in the denominator. It's going to change V sub f, and it becomes 9.1, decreases that, meters per second. And now if my depth is equal to 0.5 meters, my breakthrough time is roughly 14 hours, almost 14 and a half hours. If I increase also the depth, then it's almost 30 hours. So I just did those calculations just to give you a sense that if I just double the depth of the bed, I can a little more than double the breakthrough time. So it means that I can treat twice the volume of air or water. And then I don't have to regenerate so often. If I double the cross-sectional area and I keep that depth the same, I also can almost there I can double my breakthrough time. And then if I do both, I go from 7 hours to almost 30 hours. So I can significantly increase that breakthrough time, so I'm not having to regenerate as often. So any questions about this? No questions? Okay. Since there's no questions, we'll just move on. And I need to do a new share. Go here. Okay. So the second to the last unit that we'll study is the use of condensers. So kind of stepping back to the the beginning of the adsorption unit, we talked about, and I showed you this slide, and we focused there on this part right here. Okay, so we focused on the adsorption part of this schematic diagram. Now, as we just looked at, after a period of time when you've reached breakthrough, you then, in a regenerative system, would regenerate that column so that you can restore its usability and efficiency. And often that is done with steam. So what you end up with is a concentrated stream, gas stream, of whatever you have been removing in this adsorption column. Now, in many cases, that material is valuable. You don't want to discharge it. So what you want to try and do is design a way to recover that material. And that's where condensers are utilized. So it's simply a process that is used to lower the temperature or increase the pressure of a gas stream. The goal is to convert that material from a gas to a liquid phase and to separate the valuable substances from the gas. So these processes allow you to recover valuable material. They're relatively simple to operate, relatively inexpensive. They can also be used as pre-treatment to subsequent processes, and typically we're looking at removal efficiencies of 50 to 95%. Now, I actually thought I had what we're going to do. Thought I had added a slide in here. So what I'm going to do real quick is we're going to copy that, and paste it there, and then what I'm going to do is, again, I'm going to delete that. No, we'll just make this. No, that's not going to work. Okay, we're going to copy this. I'll try this again. Okay, we'll just leave this size. Basically, what I wanted to show you in this point, and I thought I had done this, is what we have is we have a gas stream here, and this gas stream contains toluene. Now, the freezing point of toluene is minus 95 degrees C, so we have no problem with freezing toluene. So what we're going to do is we're going to take that stream, we're going to cool it with a refrigerant, just like your food in the refrigerator is cooled and kept cool. And then what we would do is we would have a phase separator. So what we've done is we've chilled that toluene, so it's taken it from a gas phase to a liquid phase. We then have a phase separator so that we can recover the liquid toluene, reuse that, and then we would have a outlet stream. And in this case, the outlet stream contains 50 parts per million toluene. We would have to treat this, and it could be treated with a number of processes, one of which we'll talk about next week is incineration, catalytic oxidation. So that's what we'll look at next week. We can think about that in terms of this process, this phase separator, and then actually having an outlet stream. So we've used the condenser to recover that valuable toluene, and then what we couldn't recover, we could then catalytically oxidize, incinerate, or we could put an adsorption column. Condensers come in basically two different types. A contact condenser, and you can think about this essentially as the spray tower that we've talked about. In this case, the water that's sprayed, so we've got the sprays and nozzles, and what we're doing is we're spraying very cold water onto the gas stream. What we're attempting to do is to condense that material. So it essentially ends up in the aqueous stream. Surface condensers, you can think about actually a refrigeration unit, an air conditioner. Here what you have is you have gas that's contacting a cooled surface, and you can see you've got these seamless tubes. Inside that tube, you're circulating a chilled liquid or a gas, and your airstream that you're attempting to condense flows around it. So in this case, the coolant and the gas that you're treating never come into direct contact. And then that chilled vapor condenses. It can be condenses and then it's collected. And then the non-condensed vapors exit the condenser, and they would either be emitted to the atmosphere, released to the atmosphere, or treated with some other additional treatment. Typically, these are operated in series with multiple so that we can improve performance. The major challenge with these is the same challenge that we have actually with most refrigerators. It's just material freezing on the cooling coils. And this is especially problematic when you need high efficiencies. If that's the case, then the temperature is less than the freezing temperature of the material, and then that requires frequent defrosting. Not unlike a refrigerator, although we've designed automatic defrosting. Used to be you pretty much had to take everything out of the freezer, periodically defrost it, and then you could put it back in, because otherwise you ended up with a freezer compartment that was filled with ice. So it's essentially the same type of process. Where you have water vapor, that water vapor cools, freezes on the cooling coils, and again, that's going to require frequent defrosting that may contaminate the recovered liquid, and that's a problem. Another major problem is that you've chilled the gas. Okay? You waste a significant amount of energy in that chilling process. And then if you need to heat the gas again, then now you use energy in now warming up that gas. And finally, one of the major challenges, especially when you're dealing with volatile organic chemicals, is that you have to be very, very careful that the mixtures don't exceed the lower explosive limit. If they do, then you have an explosion fire hazard, and you need to take all possible precautions to avoid possible ignition sources, use flamethrowers. Flame arresters. You don't want flamethrowers. You want flame arresters to prevent any fires or explosions. As I mentioned, typically these are done with multiple units. You may see the cooling and condensation is done in stages to attempt to try and remove most of the water first, and then that means that you have less freezing of water on the coils and don't have to defrost. You won't have to defrost as regularly. So this actually is a short lecture. I could have started incineration, but I decided I would just wait and do that on Monday. So on Monday, we will finish incineration. And I'm happy to take any questions. Otherwise, what I will do is I'm going to go back to the gas slide here. And just to the reminders, again, just to remind you, participation questions is open. You've got until Sunday. You've got a homework on adsorption and incineration that is due. And just a reminder that your final report and poster are both due on the 30th. So if anybody has any questions, happy to take those. Otherwise, I will end lecture early today. Wish you a happy weekend, and then meet with you again on Monday.